Welcome to video lecture B4. This one is on the column space of a matrix. I'll be your preceptor, Tom Roby, and here are the outline and objectives. We're planning to define the column space of a matrix A. We'll show that it's a subspace, and we'll connect it with the span of the columns of A, which is actually exactly how it's defined. We'll compare and contrast the column space with the null space from the previous video lecture so that we see how they're similar and how they're different. And then we'll define the notions of linear transformation, kernel, and range for general vector spaces. This won't be very different than what you've seen already, but we need to have the notions for the more general setting. And then we'll connect them with the concepts of null space and column space when we have a linear transformation that's represented by a matrix. So that's the agenda. And so here's the definition. A matrix, we have a rectangular matrix, M by N. We'll define the column space of A to be the set of all images. If I think of the matrix A as representing, some kind of transformation, so that means I've got R to the N here, I've got R to the M over here, right? And then this is the thing that takes a vector X and sends it to A times X, right? Then the column space is the set of all things in R to the M that I can get to from some X in R to the N. So in other words, if I look at everything over here, the whole space, and I say, where did you go to over there? I mean, I know that 0 went to 0 over here. That's fine. But there's some subspace. We'll show it's a subspace in a minute, where this is the set of all things of the form A sub x, and maybe there's some stuff in R to the M that gets left out. Maybe it's all of R to the M. It can happen either way, depending on the values of M and N. So that's what I mean. So I've got x's over here, I've got y's over here. So this vector y is equal to ax. And so any y that's equal to ax for some x in R to the N is in the column space. Okay. So of course, it's easy to see, right, by the way we define vector matrix multiplication, that if y is in the column space of A, well, then it's equal to A times x for some x. But that just means it's the x linear combination of the columns of A. So that means that y is, by definition, in the span of the columns of A. And that explains the term column space. It's literally just the span of all the individual columns of the matrix. Okay, so we've got two different ways, a more conceptual linear transformation kind of way of looking at it, and a very, hands-on take linear combinations of things. And it's also important to understand that when we were looking at the null space, we were looking at all vectors over here that went to 0. And so that was a subspace of R to the N. But this is a subset of R to the M because it's all images in the target space. Let's see. So let's now look at a quick proposition, which is that this is a column space is actually a subspace of R to the M. Right? So let's think about it from first principles first. Just what's the definition of a subspace? It has to satisfy three properties, right? It has to have a 0 vector or some vector so that it's not empty. Y is 0 in the column space. Well, y is 0, the image of some x under A. Which x should it be? 0, right? A times 0 is 0. So yes, 0 is in the column space. Is the column space of A closed under vector addition? Right? So let's see if we can check that out. So suppose we know that we've got two things over here. Right? So suppose we've got, I don't know, I'll call them y and z. So suppose we know that y is equal to ax, and something else that I'll call z, suppose it's equal to A times some vector w. Right? We know that these x and w have to exist. Well, then what can you tell me about, like, if I add these two things? Well, that's equal to A times x plus w. Well, it's equal to ax plus aw, which is equal to A times a of x, a to the quantity x plus w. So therefore, y plus z is the image of x plus w. So if I have two different things over here, so x and w, and so w goes over here to z, then if I add y and z over here, I know that definitely x plus w has to go to y plus z. Okay, so it's closed under vector addition. All right, and finally, is it closed under scalar multiplication? Well, it's the same kind of argument, right? If I take like c times, I guess I can just add it in here, right? If y is equal to a times x, well then k times y is going to be equal to k times a times x, but that's just equal to a times k times x because the scalars pull through. So the point really here is that things are linear, and so that's why you get a subspace. Or you could actually, since we know that we've got this hands-on interpretation of the column space as just being the span of a bunch of vectors, you could just use the proposition from video lecture B2 that the span of a set of vectors is always a subspace, right? And we saw that just by showing these three properties, but using the fact that if you have a linear combination for one, a linear combination for another, add them, that gives you a linear combination for the sum. Okay, so this is actually a very easy proposition. And let's just take a quick look at a small example. Suppose I've got this 2 by 3 matrix, right? So it eats vectors in R3. It spits out vectors in R2. So it's going from R3 to R2 in this picture. And suppose that B is in the column space of A. Well, what does that mean? How could you know whether something? Well, let's take a look, right? B is in the column space of A means that it's sublinear combination of 1, 0, negative 2, 0, and 0, 1. But in particular, even ignoring the negative 2, 0, if I have any linear combination I want of 1, 0, and 0, 1, I get all of R2, right? Because that's the standard basis vectors for R2. So by definition, it's true if and only if B is in the span of these three vectors. But in fact, we only need like either of the first two and the second one in order to have a spanning set. So in any case, we get all of R2. So in this case, the whole thing would be shaded, right? We'd be getting everything in the codomain. So notice that while we've got it as the span of these three vectors are not linearly independent, right? Because the second vector and the first vector are scalar multiples of one another. In a lecture coming soon, we're going to be interested in having spanning sets which are as efficient as possible, which means that we don't have any of this redundancy, and we will get rid of them and have linearly independent things, and we'll call those bases. But that's for the next lecture. So now let's take a look at a quick slide where we compare the null space and the column space. So I've got my two examples. There's the matrix we just looked at. And by the way, you may remember this is the matrix in the null space matrix. We computed the null space. It took us a little while to do it. And we got that the null space of this matrix was a line in R3. Right? So line in R3 for the null space. Over here, the column space was all of R2. So these things aren't related in such obvious ways, although we'll get to something later when we have more theory that is an interesting relationship. And now here's another vector, another matrix B, which has 4 columns of length 3. So its column space must live in R3, right? And this is its row reduced echelon form in case it becomes useful later. Okay, so here's our table for comparison. So the null space of A, first big difference is the null space of A is a subset of R to the n of the domain here, whereas the column space of A is a subset of the target space, or the codomain, R to the m. The null space of A is defined implicitly. It's defined to be the set of vectors so that AX, the set of vectors such that AX equals 0, right? But that doesn't give you a very explicit description of X, whereas the column space is given explicitly as a span of a set of vectors. So what that means is that it's actually a little hard to find vectors in the null space. You have to do some work. I mean, it's just row reduction. It's work we know how to do and that we've done before, but it's not like, you just look at it and you know what to do. Whereas if I ask you, what are some vectors in the column space of B, you can say, well, 1, 3, 2, and 2, negative 1, 2, and 3, 2, 4, or you could add these two and say 3, negative 2, 4. Oh, no, that's different from 3, 2, 4. Oh, that is 3, 2, 4, right? So those, so you can get, but you could add 2 other columns that aren't and get a column that's not represented there. Okay. Whereas, right. So now let's take a look here. If we've got V is in the null space of A, if and only if AV equals 0, right? That's just the definition. V is in the column space of A, if and only if AX equals V is consistent. So if you want V to be in the null space, you have to look at where it maps, it goes to 0. If you want V to be in the column space, you look at V here, you have to be able to find an X so that AX equals V. So you have to have a consistent equation there. So they can both be defined in terms of the equation A blah equals blah, but they're on different sides of that equation. So given a vector V, it's easy to check. It might be hard to find vectors if you don't know anything, but if I ask you, is this vector in the null space of A, you can check really easily, right? Because all you have to do is apply A to it and see whether it works or not. So for example, right, I could say, well, is 2, 1 0 in the null space of A? And you would say, all right, well, when I apply 2, 1, 0, apply this matrix at 2, 1, 0, I get 2 minus 2, 0. I get 0 in the top, and then I get 0, 0, 1 times 0, 0. So I do get 0, 0, and so you say, yes, it is. Okay? But if I take in like 2, 1, 1, then you can check that you multiply by A, you don't get 0, so it's not in the null space. On the other hand, it's not so easy to check whether V is in the column space of a matrix. Because if I want to know whether if I take some vector of size 3 and I want to check whether it's in the column space, I need to know whether I can write it as a linear combination of these columns. That translates into solving a system of linear equations. So I'm back to needing to do some row reduction. So when I say hard here, I just mean as hard as row reduction, not wicked hard or anything. Okay, so finally, got one or two more. The null space of A is 0. So let's look at extreme cases. The null space of A, 0 goes to 0, right? So the null space of A can be no smaller than 0, and it can be no bigger than the whole thing. You could have the linear transformation that sends everything to 0, right? That's just the 0 matrix. So that's one extreme case. But the extreme case where the null space is 0, that's true if and only if AX equals 0 has only the trivial solution, right? So this is the homogeneous equation, is only the trivial solution. And the extreme case that we want to consider over here is the column space could be everything. It could be 0 if you send everything to 0, so you've got that same other extreme case. So the 0 matrix gives you the other extreme case where everything is in the null space and only 0 is in the column space. So maximally big here, maximally small here. But now we're looking at maximally small here and maximally big here. So maximally small here means that AX equals 0 is only the trivial solution, and maximally big here means that AX equals B is consistent for every B. That's just by definition. Okay, but here's something slightly more interesting. The null space of A equals 0 if and only if the linear transformation x goes to AX is 1 to 1. And the column space is maximal if and only if the linear transformation is onto. So remember we had 1 to 1 and onto before. So this one, the column space being r to the m if and only if the linear transformation is onto, is really just a definition, right? Because we know the column space is the set of all things that get mapped to. So if you map to everything r to the m, then you're onto. And if you're onto, you must be mapping onto r to the m. But this one is the only one that takes a couple minutes thought. But we've seen the argument before in the invertible matrix theorem for square matrices. Turns out that it's fine for this case too. So how do you deal with this? Well, you say, suppose I want to show that it's 1 to 1, right? So suppose that A times V is equal to A times U. That I've got two vectors, U and V, and they go to the same place. Then I want to show that U and V had to be the same to begin with, right? Because what I don't want for 1 to 1 means that different things here go to different things there. And so I'm saying, suppose I had U and V and they both went to the same thing, I want to claim they had to be the same to begin with, right? So, but here's the argument. If AV equals AU, well, that's equivalent to saying that A times V minus U equals 0, right? But so now, I know the null space is 0. Right? So if I know the null space is 0, then if a times something equals 0, then that something must be 0. So this implies that v minus u equals 0, which implies that v equals u. Okay, so therefore 1 to 1. So that's showing that if the null space is trivial, then the linear transformation is 1 to 1. Of course, the other way is clear, because if a linear transformation is 1 to 1, then that means we know that 0 is in the null space. We know that a0 equals 0. And so if it's 1 to 1, that can be the only thing that goes to 0. So really saying the null space of a is 0 is saying that a is 1 to 1 at 0, but linearity lets you translate that property to being 1 to 1 everywhere. So that's very similar to an argument we did for the invertible matrix theorem. So two other things I'd like to note here. One is that notice that it was hard to find vectors in one, but easy to check. And the other one, it was easy to find, but hard to check. So you got this kind of dichotomy going on there. And the other thing I'd like to notice is that for the invertible matrices, 1 to 1 and onto were equivalent to each other by the invertible matrix theorem. It's because we have rectangular matrices that the linear transformation being 1 to 1 is not, if and only if the linear transformation is onto. But for an invertible matrix, we'll always have a trivial null space, and you'll always be able to get everywhere. You'll always have a full column space. So now let's take a look at these two examples, right? This matrix is onto, as we saw. We got all of our 2. But it's not 1 to 1, because, for example, if I apply, if I take negative 2, 0, 0 to this matrix, then I'm just taking negative 2 times this column, 0, 0, I'll get negative 2, 0. And if I apply 0, 1, 0, linear combination, then I'll get negative 2, 0. So it's clear that it's onto, but not 1 to 1. You can check that B is actually neither 1 to 1 nor onto. Because, for example, if you look at 1, 3, 2 and 2, 6, 4, that's a multiple of one another. So I could again take like 2, 0, 0, 0 would give me 2, 6, 4, and 0, 0, 0, 1 would give me 2, 6, 4. Or you could notice that like the sum of this and this gives me this. So 1, 1, 0, 0 would give me the same output as 0, 0, 1, 0. Okay? As far as the null space goes, so for B, the column space, so the linear transformation is not 1 to 1. And we can see that the column space actually is just going to be two-dimensional, because this vector doesn't give us anything new, this vector doesn't give us anything new, and so it's really just these two vectors that generate the column space of B. On the other hand, the null space of B is also going to be two-dimensional, right? Because we've got two free variables, x3 and x4, written in terms of the pivot variables x1 and x2. So maybe I'll just write that down. So for B, the column space of B is equal to the span of just the first two columns, 1, 3, 2, and 2, minus 1, 2. And the null space is the span of two vectors, which I'll just call v1, v2, because I don't want to write them down now, but you know how to take that and translate it into a solution. Okay. Okay, so the last brief topic that I want to address here is that we define linear transformations between Euclidean spaces, r to the n and r to the m, but we need to have the notion more generally. So I'm just going to define it here, but it's the same thing we've seen before. So if I've got two arbitrary vector spaces, which could be, vector spaces of functions or matrices or polynomials or whatever I happen to be interested in, I'll call a function a linear transformation if it satisfies the two linearity axioms, if it preserves addition and scalar multiplication. So this is all really similar to what we've done before, and I didn't even really want to bother defining it, except that I need to in order to give you some notation that you'll see other places in the literature. So if you've got a linear transformation, then people often use the term kernel to mean the set of all vectors that get sent to 0. And they mean the range, they'll call the range to be the set of all vectors that you can get using all the inputs that you have in V, the set of all vectors in W. So this is a subset of W. So it's the same picture that we had before, where you've got, some, right, the blobs haven't changed very much. They just have different names, right? So I've got V here and W there, and I've got my linear transformation T that goes from one to the other. And so now the kernel is going to be, some things go to 0, right? So there's a 0 vector over here. And anything that goes to 0, including the 0 vector here, right, that's all the null space. Sorry, not the null space, the kernel of T. On the other hand, you can look at everything that you mapped to throughout all of V. And so that could be, maybe all of this stuff. Of course, it'll have to include 0 because it's subspace. And so that will be what's called the range of T. Okay, so these are all very natural names. And the main point of all this is that if you're in a situation where your linear transformation is given by a matrix, then the kernel of T is just the null space of A, and the range of T is just the column space of A. Okay, so that's all there is to it. We don't really need two different names for the same thing, except that this is the one term that's used for linear transformations, and sometimes we'll need to be considering generalized linear transformations. And all of these terms are widely used: null space, column space, kernel, and range. So you might as well just get used to them. So the point is that the kernel of T, if it's given by a matrix, then this will be the null space of A. And if this is given by a matrix, this will be the column space of A. But it's not necessarily given by a matrix. Okay, so that's all I wanted to say, and this seemed to be the right place to squeeze it in at the end of this lecture where we're talking about null spaces and column spaces. So that's it for this video lecture. Thank you for your kind attention.